Okay, so for this deep dive, we're going to unpack what is really the nervous system of modern media.
Exactly. We're talking about the infrastructure that underpins, well, everything that's live.
Professional video transport, how you move these massive, uncompressed digital signals over, huge distances just using light.
And to do that, we're going to focus on one specific piece of gear. It's the Thor Broadcast F-2SDI-B-3G-TXRX-RM unit.
Right. And by understanding this one system, you really start to see the engineering choices that define live broadcast, electronic news gathering, all of it.
The mission for this hardware is, it's incredibly tough.
It has to handle serial digital signals, right? Up to 3G-SDI.
Which means it's transmitting data at a blistering 3.0 gigabits per second.
And here's the kicker, the part that it's hard to wrap your head around. It does all of that on one single strand of optical fiber.
That really gets to the core challenge. When you're moving uncompressed video, especially for something like live sports, what the industry calls ENG,
electronic news gathering,
you need enormous bandwidth and absolutely zero degradation. Copper cable just can't do that over distance. It's not even an option. So fiber is. It's mandatory.
But laying fiber is incredibly expensive. So the real game here isn't just speed, it's density. How on earth do you squeeze two channels of data going in opposite directions, bidirectional onto that one tiny strand?
That's where the magic is, both technically and economically. The technology is called CWDM.
Coarse wavelengths division multiplexing.
Exactly. CWDM lets you treat that single physical fiber not as one pipe, but as many. It uses different colors of light, different wavelengths to carry separate data streams so they don't interfere.
And it scales up, right? This unit is 2 channels, but the tech can do more.
A lot more. The underlying CWDM technology can be configured for up to 16 total channels on that one fiber.
16? Wow.
And if you need even more density, there are custom DWDM systems that can push that up to, believe it or not, 160 channels.
It's a staggering ROI for a single cable run.
It is. And what's fascinating is how they maintain stability over those distances. The units are using high-quality DFB lasers, distributed feedback lasers.
So these aren't just standard emitters.
Not at all. They provide the spectral stability you need to go the distance. So an off-the-shelf model can function perfectly up to 50 kilometers on standard single-mode fiber.
Okay, 50 kilometers, that's a really long run.
Yeah.
That has to be enough distance for noise and timing drift for jitter to just corrupt the signal completely. So how does the hardware fix that?
That is the critical question. And the solution is automatic reclocking. Jitter is essentially, noise and the timing of the digital pulses.
Right.
Reclocking strips all of that out. It completely rebuilds the digital signal's timing from scratch right at the output. It's like a reset button for the signal.
So you get a clean, professional-grade signal every single time.
Guaranteed.
That reliability has to extend to compatibility, too. I mean, an ENG team out in the field is mixing gear from different vendors all the time.
Oh, absolutely. And that's built in. Beyond just adjusting to any signal type from, say, 1 megabit up to 3 gigs, the units use industry-standard internal CWDM modules.
Which means they can talk to other systems.
It ensures they can play well with similar systems from other big manufacturers. They can even interoperate with some of those highly specialized proprietary systems like Python systems.
So at the end of the day, what we have here is this single one-rack unit box that's really the backbone for high-density global media.
It's the definition of a resilient backbone.
We mentioned the operational temperature range is pretty wide, minus 10 Celsius to plus 55 C. So think about that for a second. If you're an ENG team, this 15-pound kit might be in the back of a truck in a desert.
In the middle of nowhere, yeah.
Pushing 16 uncompressed signals across 50 kilometers, and it has to work perfectly at that 55 degrees C limit. The resilience is it's designed into the core architecture.
Which brings up a really interesting question for the future. We've seen how CWDM maximizes the fiber we already have, but as video compression gets better and IP transport gets more common, will we still be relying on uncompressed SDI transport like this for live contribution in, say, a decade?